You don't understand gravity. Neither do I. Neither does anyone. Not your physics teacher. Not Stephen Hawking. Not Einstein. Not Newton. Nobody. And I'm not being dramatic. I'm being precise. You experience gravity every single moment of your life. When you drop your phone, gravity pulls it down. When you walk, gravity holds you to the ground. When you sleep, gravity keeps you from floating away. It's the most familiar force in the universe, the most obvious, the most constant. And we have absolutely no idea what it is. We can describe how it behaves. We have equations that predict its effects with 15 decimal places of precision. We use it to launch satellites, land spacecraft on Mars, and navigate billions of kilometers through space. But we cannot explain what gravity fundamentally is. Why does mass attract mass? What carries the gravitational force? Why does it exist at all? We don't know. Every other fundamental force, we know what it is. Electromagnetism? Carried by photons, particles of light that transmit the electromagnetic force between charged objects. The strong nuclear force? Carried by gluons, particles that bind quarks together inside protons and neutrons. The weak nuclear force? Carried by W and Z bosons, particles that mediate radioactive decay. Gravity? No idea. We don't know what carries it. We don't know why it exists. We can't make it fit with the rest of physics. And when we try, the mathematics explodes into nonsense. This isn't a minor gap in our knowledge. This is the deepest, most embarrassing mystery in all of fundamental physics. And I'm going to show you exactly why gravity is so mysterious, why every attempt to explain it has failed, and why solving this problem could change everything we know about reality. Because the force that holds you to this planet, that shapes galaxies, that governs the entire cosmos, we don't understand it. And that should terrify you, or excite you, probably both. Let me be specific about what we can and cannot do with gravity. What we can do, we can launch satellites into orbit with millimeter precision. The GPS satellite constellation orbits at exactly 20,200 kilometers above Earth. We put them there using gravitational calculations. They stay there because we understand orbital mechanics perfectly. We can predict planetary positions centuries in advance. Astronomers calculated where Jupiter would be on January 1st, 2100. They know to within a few kilometers, because Newton's equations work. We can detect gravitational waves from colliding black holes 1.3 billion light-years away. LIGO measured ripples in spacetime, distortions smaller than a proton, caused by two black holes merging. We predicted what the signal would look like. We found it, exactly as expected. We can calculate the expansion rate of the entire universe. Using general relativity, cosmologists measure how fast space itself is stretching. They determine the universe's age, composition, and fate. With precision. What we cannot do, we cannot explain what causes gravity at a fundamental level. Why does mass create gravitational attraction? What's the mechanism? We have no answer. We cannot unify gravity with quantum mechanics. The other three forces fit into quantum field theory beautifully. Gravity doesn't. The math breaks. Infinities appear. The theory collapses. We cannot predict what happens at the center of a black hole. General relativity says there's a singularity, a point of infinite density. But infinite density means the theory has failed. We literally don't know what's there. We cannot explain why gravity is so weak compared to other forces. Electromagnetism is 10 to the power of 36 times stronger than gravity. Why? No idea. Let me emphasize how absurd this is. We use gravity to navigate spacecraft across billions of kilometers of space. We rely on it for technology that works every single day. GPS would fail without accounting for gravitational time dilation. And we don't know why gravity exists. This isn't philosophy. This is a crisis that's been ongoing for more than 300 years. Here's where we're going. Act 1 is where we are now, confronting the paradox. Gravity is the most familiar force, and we don't understand it. We can predict how it behaves, but we can't explain what it is. Act 2 will look at Isaac Newton. In 1687, he gave us the universal law of gravitation. It's one of the most successful equations in the history of science. It predicts planetary motion, tides, orbits, everything. But Newton himself admitted he couldn't explain what causes gravity. His equations describe what it does, not what it is. And he knew that was a problem. Act 3 will explore Einstein's revolution. In 1915, Albert Einstein proposed something radical. Gravity isn't a force at all. It's the curvature of spacetime. Mass bends space and time, and objects follow the curves. This is general relativity. It's mind-bending. It's beautiful. It makes predictions that have been confirmed over and over. And it still doesn't answer the question, what is gravity? Why does mass curve space-time? Einstein gave us geometry. He didn't give us explanation. Act 4 is where things fall apart. When we try to make gravity compatible with quantum mechanics, the physics of the very small, everything breaks. Quantum field theory works perfectly for the other three forces. But when we apply it to gravity, the math produces infinities. Nonsense. The equations explode, and we don't know how to fix it. Act 5, we'll look at the attempts to solve this. String theory, loop quantum gravity, dozens of other approaches, brilliant ideas, elegant mathematics, 70 years of work by thousands of physicists, and zero experimental confirmation. Every theory either makes no testable predictions or predicts things we can't measure. We're stuck. Act 6 is the reckoning. What does it mean that we don't understand gravity? Why does this matter? What's at stake? And what comes next? This is going to challenge everything you think you know about physics. Because the story you were told, that science has explained the universe, that we understand the fundamental forces, is incomplete. Gravity is the exception, the outlier, the mystery. And it's the most important force in the cosmos. By the end of this, you'll understand why physicists lose sleep over gravity. Why it's the holy grail of theoretical physics. Why solving it could unlock the deepest secrets of reality. But you'll also understand why we might never solve it. Why the answer might be beyond our current framework. Why we might need a revolution as profound as relativity or quantum mechanics to even ask the right questions. The universe is held together by a force we don't understand. Let that sink in. Now let's start with the first person who tried to explain gravity and his honest confession that he failed. England, 1687. Isaac Newton publishes Philosophia Naturalis Principia Mathematica, Mathematical Principles of Natural Philosophy. It's one of the most important books ever written. In it, Newton presents the universal law of gravitation, a single equation that describes how every object in the universe attracts every other object. It works for falling apples. It works for orbiting moons. It works for planets circling the sun. It works for galaxies rotating through space. One equation. Universal applicability. It's a triumph of human intellect, a unification of celestial and terrestrial mechanics, proof that the same laws govern Earth and the heavens. And Newton knew, explicitly, consciously, that it didn't explain what gravity actually is. He could describe how mass attracts mass. He couldn't explain why. And that bothered him deeply. But his equations worked so perfectly, so universally, that for more than 200 years, physicists accepted them without demanding a deeper explanation. "Shut up and calculate," they essentially said. "The math works, that's enough." But it wasn't enough. Not really. Because buried in Newton's success was a profound mystery. A question that couldn't be answered. A gap in understanding that haunts physics to this day. Let me show you what Newton discovered, and what he couldn't explain. Act 2. Newton's Triumph and Failure. Isaac Newton's universal law of gravitation is deceptively simple. F equals G, open parenthesis, m1, m2, close parenthesis, divided by r squared. That's it, one equation. Let me break down what it says. F is the gravitational force between two objects. m1 and m2 are the masses of those objects. R is the distance between them. G is the gravitational constant, a number that makes the units work out. About 6.67 times 10 to the power of negative 11 in standard units. The equation says, every mass attracts every other mass. The strength of that attraction is proportional to the product of the masses, and inversely proportional to the square of the distance between them. Double the mass, double the force. Double the distance, force drops to 1/4. Simple, elegant, universal, and stunningly accurate. Here's what Newton's equation predicts. Planetary orbits. Johannes Kepler had already discovered that planets move in ellipses, not circles. But he didn't know why. Newton's law derives Kepler's laws from first principles. The elliptical orbits fall naturally out of the inverse square law of gravity, tides. The moon's gravity pulls on Earth's oceans more strongly on the near side than the far side. This creates bulges, high tides. Newton calculated this, predicted it, explained the daily rhythm of the ocean. Comets. Edmund Halley used Newton's equations to predict that a comet he observed in 1682 would return in 1758. It did, exactly on schedule. We call it Halley's Comet now. Satellite motion. Centuries before satellites existed, Newton understood that if you threw something fast enough horizontally, it would fall around the Earth instead of into it. He calculated the orbital velocity needed. When we launched Sputnik in 1957, we used Newton's equations: galaxy rotation, star clusters, binary stars, gravitational lensing precursors. Everything from small scales to cosmic scales, Newton's law works. This is one of the most successful equations in the history of science. For more than 200 years, it was essentially perfect. No failures, no exceptions, just universal applicability. But here's the thing. Newton understood, and here's what most people miss when they learn about gravity in school. The equation describes what happens. It doesn't explain why it happens. Newton knew this, and it bothered him profoundly. Newton's law tells you that the Earth pulls on the Moon with a force proportional to their masses and inversely proportional to the square of the distance between them. But it doesn't tell you why. Why does mass attract mass? What's the mechanism? How does the Earth know the Moon is there? Newton couldn't answer these questions, and he was honest about it. In letters and in later editions of the Principia, Newton wrote, and I'm paraphrasing here because the original is in Latin, "I have explained the phenomena of the heavens and of our sea by the force of gravity, but I have not yet assigned a cause to gravity. I do not make hypotheses about what I cannot demonstrate." Translation: My equations work, but I don't know why gravity exists. This wasn't false modesty. This was intellectual honesty. The problem Newton identified is called action at a distance. The Earth and the Moon are separated by 384,000 kilometers of empty space. There's nothing between them, just vacuum. And yet, somehow, the Earth pulls on the Moon, and the Moon pulls on the Earth. How? If there's no physical connection, no rope, no rod, no medium, how does the gravitational force cross that empty space? Newton's equation says, it just does. The force exists. Here's the formula. But that's not an explanation. That's a description. Think of it this way. If I push a cart, you understand the mechanism. My hand touches the cart. Molecules in my hand push against molecules in the cart. Forces transfer through contact. Mechanical. Understandable. But gravity? The sun pulls on the Earth across 150 million kilometers of nothing. No contact, no medium, no mechanism, just attraction. Newton found this deeply unsatisfying. He even called it absurd in private correspondence. The idea that one object could affect another across empty space, with nothing mediating the interaction, seemed philosophically problematic. But the math worked. So Newton published the equation, admitted he couldn't explain the cause, and moved on. And for 200 years, physicists accepted this state of affairs. The equation is so good, so accurate, that the mystery of how gravity works got swept under the rug. But the mystery didn't go away. It festered. By the late 1800s, cracks started to show. Not in Newton's predictions, those were still perfect for almost everything, but in the conceptual foundation. Problem 1. Instantaneous action at a distance. According to Newton's law, if the sun suddenly disappeared, the Earth's orbit would change instantly. The gravitational force would vanish the moment the sun vanished. No delay, no travel time. Instantaneous effect across 150 million kilometers. This started to bother physicists in the 19th century, because by then they understood that light takes time to travel. About 8 minutes from the sun to Earth. If the sun disappeared, we'd still see it for 8 minutes, because the light was already on its way. But gravity? Newton's theory says the gravitational change would be instant. That seemed wrong. How could gravity propagate faster than light? How could anything? Problem 2. No mechanism, no medium. In the 1800s, physicists thought light traveled through a medium called the luminiferous ether, an invisible substance that permeated space and carried light waves. They were wrong about the ether, but at least they were trying to explain how light propagated. Gravity? No one even proposed a mechanism. It was just mass attracts mass, with no explanation. Some physicists tried to invent gravitational ethers or gravitational fluids. None of the ideas worked. None made predictions. They were just storytelling. Problem 3. Incompatibility with special relativity. In 1905, Albert Einstein published his special theory of relativity. One of the key insights: nothing can travel faster than the speed of light. Not particles, not information, not any causal influence. The speed of light, about 300,000 kilometers per second, is the cosmic speed limit. It's absolute. But Newton's gravity is instantaneous. It propagates infinitely fast. That's a direct contradiction. Einstein's relativity says, information cannot travel faster than light. Newton's gravity says, gravitational effects are instantaneous. Both can't be true. Something had to give. And what gave was Newton's theory. Not because it was wrong. It's still correct for almost everything we experience in daily life, but because it was incomplete. It described gravity's behavior perfectly, but it didn't explain what gravity is. And when pushed to extremes, very strong gravity, very high speeds, It broke down. The equation worked. The conceptual foundation didn't. For more than 200 years, Newton's law of gravitation reigned supreme. It worked for cannonballs falling on Earth. It worked for planets orbiting the Sun. It worked for binary stars orbiting each other. It worked for everything. But three problems lingered. 1. Action at a distance. No mechanism for how gravity crosses empty space. 2. Instantaneous propagation. Gravitational effects are instant, which seems impossible. 3. Incompatibility with relativity. Nothing should travel faster than light, but Newton's gravity does. And underneath all of this was the deeper question Newton himself couldn't answer. What is gravity? Not, how does it behave? We know that. Newton told us. But what is it fundamentally? Why does mass attract mass? What causes the force? What carries it through space? No one knew. And then, in 1915, Albert Einstein published his general theory of relativity. And he gave an answer so radical, so geometrically beautiful, so counterintuitive, that it took decades for physicists to fully accept it. Einstein said, "Gravity isn't a force at all. Let me repeat that, because it's important. Gravity is not a force. It's something else entirely, something stranger, something that requires rethinking the nature of space and time themselves." Einstein proposed that gravity is the curvature of space-time. Mass doesn't pull on other mass. Mass bends the fabric of space and time, and objects move through that curved space, following paths that look like they're being pulled, but actually aren't. There's no force, no pulling, no attraction, just geometry. This sounds insane, because it is, but it's also correct. And I'm going to show you exactly what Einstein meant, how he came to this conclusion, and why it's one of the most profound insights in the history of physics. But I'm also going to show you why, despite being correct, it still doesn't answer the fundamental question. Because Einstein's general relativity describes how mass curves space-time. It doesn't explain why mass curves space-time. We've traded one mystery for another. Imagine you're standing on a trampoline. The fabric is flat, taut, stretched. Now place a bowling ball in the center. The fabric dips, curves, creates a depression. Now roll a marble across the trampoline. The marble doesn't travel in a straight line. It curves towards the bowling ball. Not because the bowling ball is pulling it, but because the fabric itself is curved. The marble is following the straightest possible path through curved space. That's gravity, according to Einstein. Space and time are the trampoline. Mass is the bowling ball. And everything else, planets, light, satellites, are the marbles, following curved paths through curved space-time. No force, no pulling, just geometry. This is general relativity, and it's one of the most beautiful, most experimentally confirmed theories in all of physics. But here's what keeps physicists up at night. It describes the curvature. It predicts how mass affects space-time. It works perfectly, but it doesn't explain why mass curves space-time. What's the mechanism? What connects mass to geometry? Einstein gave us new equations. He gave us a new framework. He gave us a geometric description of gravity, but he didn't give us an explanation of what gravity fundamentally is. The mystery deepened. Let me show you Einstein's revolution, and then I'll show you why it's not the end of the story. Act 3. Einstein's revolution. Albert Einstein's general theory of relativity, published in November 1915, makes a radical claim. Gravity is not a force. Mass doesn't pull on other mass. There's no attractive force, no action at a distance, no mysterious influence crossing empty space. Instead, mass curves space-time. and objects move through that curved spacetime, following what are called geodesics, the straightest possible paths through curved geometry. Let me use the analogy I mentioned earlier. Imagine a trampoline stretched flat. This represents flat spacetime, no mass, no curvature. Now place a heavy bowling ball in the center. The trampoline fabric dips, curves, creates a depression around the ball. This depression represents curved spacetime around a massive object. Now, roll a marble across the trampoline from the side. The marble doesn't travel in a straight line. It curves toward the bowling ball. It might even spiral around it before rolling away, or fall into the depression entirely. Why does the marble curve? Not because the bowling ball is pulling it. There's no rope, no magnetic attraction, no force. The marble curves because the fabric itself is curved. The marble is following the straightest possible path through curved space. That path just happens to curve toward the bowling ball. That's gravity. Earth isn't pulling you down. Earth's mass has curved spacetime around it. You're following a geodesic through that curved spacetime. The straightest path happens to be toward Earth's center. When you stand on the ground pushes up on you, preventing you from following that geodesic. You feel that push as your weight. In free fall, when you jump, or when astronauts orbit Earth, you're following a geodesic. You feel weightless, not because there's no gravity, but because you're moving freely through curved spacetime. Orbits aren't objects being held by gravity. Orbits are objects following curved paths through curved spacetime. The moon isn't being pulled around Earth. The moon is moving in a straight line through spacetime that Earth has curved. That straight line through curved spacetime looks like a circle from our perspective. This is Einstein's insight. Gravity is geometry. And it's not just space that curves. Time curves too. Near massive objects, time runs slower. This is gravitational time dilation. Spacetime, the unified four-dimensional fabric of space and time, is curved by mass and energy. And everything moves through that curved fabric. No force required. This sounds like philosophy, like abstract mathematics, like untestable speculation, but it's not. Einstein made specific testable predictions, and every single one has been confirmed. General relativity made predictions that differed from Newton's law, tiny differences in most cases, but measurable. Let me show you 4 predictions that proved Einstein was right. Prediction 1. Light bends around massive objects. Einstein's equations say that light doesn't just travel in straight lines. Near massive objects, space-time is curved. Light follows that curvature. So starlight passing near the sun should bend slightly. The sun's mass curves space-time, and light follows that curve. Newton's gravity also predicts light bending, but by half as much. So this was a crucial test. In 1919, during a solar eclipse, British astronomer Arthur Eddington measured the positions of stars near the sun. During the eclipse, stars became visible right next to the sun's edge, and their positions were shifted, exactly as Einstein predicted, twice the deflection Newton's theory predicted. This measurement made Einstein world famous overnight. Headlines declared, "Revolution in science, new theory of the universe." And it was true. General relativity was confirmed. Newton's gravity was incomplete. Prediction 2. Gravitational time dilation. Einstein's theory says time runs slower in stronger gravitational fields. Near Earth's surface, time runs slightly slower than at high altitude. The difference is tiny. For every day at Earth's surface, a clock in orbit gains about 38 microseconds. But it's measurable, and it's essential for GPS satellites. GPS works by timing radio signals from satellites. The satellites know their positions and broadcast the time. Your phone receives signals from multiple satellites, but the satellites are in orbit, where time runs faster than on the ground. If we didn't account for gravitational time dilation, GPS would drift by about 10 kilometers per day. Every GPS satellite applies Einstein's corrections. General relativity isn't abstract theory. It's in your phone. Prediction 3. Gravitational waves. Einstein's equations predict that accelerating masses create ripples in spacetime. Gravitational waves. Like dropping a stone in a pond creates ripples on the water surface. Accelerating masses create ripples in the fabric of space-time itself. These ripples travel at the speed of light, carrying energy away from the source. Einstein predicted this in 1916, but gravitational waves are incredibly weak. He thought we'd never detect them. He was wrong. On September 14th, 2015, the LIGO detectors in Louisiana and Washington state detected a gravitational wave from two black holes, each about 30 times the mass of the Sun, spiraling into each other and merging 1.3 billion light-years away. The signal lasted less than a second. The distortion of space-time was smaller than a proton, but it was there. And it matched Einstein's predictions exactly. The frequency, the amplitude, the waveform, everything. Since then, LIGO has detected dozens of gravitational wave events, black hole mergers, neutron star collisions. Each one confirms general relativity with extraordinary precision. Prediction 4. Black holes. Einstein's equations predict that if you compress enough mass into a small enough volume, space-time curves so extremely that nothing, not even light, can escape. The boundary where escape becomes impossible is called the event horizon. The object is called a black hole. Carl Schwarzschild discovered this solution to Einstein's equations in 1916 while serving in World War I. Einstein thought black holes were mathematical curiosities, not real objects. But they're real. In 2019, the Event Horizon Telescope, a global network of radio telescopes working together, imaged the shadow of a supermassive black hole in the galaxy, M87. The image shows a dark circle, the black hole's shadow, surrounded by a glowing ring, light from hot gas orbiting just outside the event horizon. The size of the shadow matches Einstein's predictions to within 17%. The shape matches. The asymmetry in brightness, because of relativistic beaming, matches. Black holes exist. They behave exactly as Einstein's equations predict. General relativity has passed every experimental test for more than 100 years. It works. It's correct. And yet, Einstein gave us a geometric description of gravity, space-time curvature, geodesics, beautiful mathematics. But he didn't answer the fundamental question: why does mass curve space-time? His equations, the Einstein field equations, relate the curvature of space-time, on one side, to the distribution of mass and energy, on the other side. They're gorgeous. 10-coupled nonlinear partial differential equations. They describe precisely how matter curves space-time, but they don't explain why this relationship exists. What's the mechanism? What connects mass to geometry? Why does putting mass somewhere cause space-time to curve? Einstein's theory is silent on this. Compare this to electromagnetism. When you ask, why do opposite charges attract? Quantum electrodynamics gives an answer. They exchange photons. Virtual photons pop into existence, travel between the charges, and mediate the force. You can visualize it, calculate it, test it. When you ask, why does mass curve space-time? General relativity says, "It just does. Here are the equations." That's not an explanation, that's a description. Einstein knew this. In his later years, he spent decades trying to unify gravity with electromagnetism, trying to find a deeper theory that would explain both as manifestations of something more fundamental. He failed, not because he wasn't brilliant, but because the problem is hard. Maybe the hardest problem in physics. General relativity describes the relationship between mass and spacetime curvature. It predicts gravitational effects with extraordinary accuracy, but it's phenomenological. It describes what happens, not why. Just like Newton's law. Newton described how masses attract. Einstein described how masses curve spacetime. Neither explained the fundamental nature of gravity. And then quantum mechanics arrived and made everything worse. While Einstein was developing general relativity in the 1910s, another revolution was brewing. Quantum mechanics, the physics of the very small, was emerging from the work of Planck, Bohr, Heisenberg, Schrödinger, and others. By the 1930s and 1940s, quantum mechanics had become the most successful theory in physics. It explains atoms, molecules, chemistry, solid-state physics, nuclear reactions, and essentially all of the microscopic world. And crucially, quantum mechanics explains the other three fundamental forces. Electromagnetism became quantum electrodynamics, QED. In the 1940s, physicists developed QED, a quantum field theory of electromagnetism. The electromagnetic force is mediated by photons. Charged particles exchange photons, and this exchange creates attractive or repulsive forces. QED predicts the electron's magnetic moment to 12 decimal places. It's the most precisely tested theory in history. The strong nuclear force became quantum chromodynamics, QCD. In the 1970s, physicists developed QCD, a quantum field theory of the strong force. Quarks are bound together by gluons. The math is harder than QED, but it works. We can calculate proton masses, nuclear binding energies, and particle collision outcomes. The predictions match experiments. The weak nuclear force became electroweak theory. In the 1960s to 70s, physicists unified electromagnetism and the weak force into a single, electroweak theory. The weak force is mediated by W and Z bosons. This theory predicted the Higgs boson, discovered at the Large Hadron Collider in 2012. The result? The standard model of particle physics. Three forces, electromagnetism, strong, and weak, unified in a quantum field theory framework. The predictions are extraordinarily precise. The standard model has been tested in thousands of experiments. It works perfectly. And then there's gravity. Gravity doesn't fit into the standard model. We don't have a quantum theory of gravity. We can't make it work. And this is a crisis, because we have two fundamental theories of physics. One, general relativity, describes gravity as curved spacetime. Classical, deterministic, smooth geometry. Two, quantum mechanics, describes the other three forces as quantum fields with particle mediators. Probabilistic, quantized, inherently uncertain. Both theories work perfectly in their domains. General relativity works for planets, stars, galaxies, black holes, anything with weak gravity and large scales. Quantum mechanics works for atoms, molecules, particles, anything with small masses and quantum effects. But there are situations where both should apply. The center of a black hole, extreme gravity plus quantum scale. The Big Bang, all mass energy in tiny volume. The Planck scale, 10 to the power of negative 35 meters, where quantum gravity effects dominate. At these extreme conditions, we need a theory that includes both general relativity and quantum mechanics. We need quantum gravity, and we don't have it, because when we try to make gravity quantum, when we try to treat it the same way we treat the other forces, the mathematics explodes, infinities appear, predictions become nonsensical, the theory collapses. For 70 years, physicists have tried to solve this. Thousands of brilliant minds, decades of work, billions in research funding, and we've failed. Let me show you why. You've just seen Einstein's revolution. Gravity isn't a force, it's the curvature of space-time. Mass bends space and time. Objects follow geodesics through curved geometry. This is confirmed by 4 major predictions. 1. Light bending around the sun, measured in 1919. 2. Gravitational time dilation, essential for GPS. 3. Gravitational waves, detected by LIGO in 2015. 4. Black holes, imaged by Event Horizon Telescope in 2019. General relativity is one of the most successful theories in physics. It's correct, it works, but it doesn't explain why mass curves space-time. It describes the relationship. It doesn't explain the cause. And when quantum mechanics entered the picture, things got much worse, because the other 3 forces, electromagnetism, strong, weak, all fit into quantum field theory. They have particle mediators. They make precise predictions. They work. Gravity doesn't fit. We can't quantize it. We can't make it compatible with quantum mechanics. And in extreme situations, black hole centers, the Big Bang, the Planck scale, both theories should apply, but they contradict each other. We need quantum gravity, a theory that unifies general relativity and quantum mechanics. And when physicists tried to build that theory, the math broke. Infinities appeared. Nonsensical results. Mathematical disaster. This is the quantum gravity problem, the deepest unsolved problem in fundamental physics. Let me show you exactly what goes wrong when we try to make gravity quantum, and why every attempt to fix it has failed. Act 4. The quantum problem. Here's the logic that seems inescapable. The other 3 fundamental forces are quantum. They're described by quantum field theory. They have particle mediators that carry the force. Electromagnetism is carried by photons. When 2 electrons repel each other, they're exchanging virtual photons. Those photons mediate the electromagnetic force. The strong nuclear force is carried by gluons. Quarks inside protons and neutrons exchange gluons. That's what holds atomic nuclei together. The weak nuclear force is carried by W and Z bosons. These particles mediate radioactive decay and certain particle interactions. 3 forces, 3 sets of force-carrying particles. All beautifully described by quantum field theory. So the logical expectation is, gravity should work the same way. Gravity should be carried by particles. We even have a name for them. Gravitons. If gravitons exist, they would work like this. 2 masses attract each other because they exchange gravitons. These particles carry the gravitational force between objects, just like photons carry electromagnetism. The graviton would be massless, like the photon. It would travel at the speed of light. It would have a quantum property called spin 2, which determines how it couples to matter. And if we could detect individual gravitons, we'd have a quantum theory of gravity. Gravity would fit into the standard model alongside the other forces. Problem solved. Physics unified. Nobel Prizes all around. Except there's one issue. When physicists tried to build this theory, when they applied the mathematical machinery of quantum field theory to gravity, everything broke. The calculations produced infinities, nonsensical results, mathematical garbage, and no one knows how to fix it. Let me explain what goes wrong when we try to quantize gravity. Quantum field theory works by calculating probabilities. You want to know the probability that two electrons scatter off each other? You calculate all the possible ways they could exchange photons. But all possible ways is infinite. An electron could exchange one photon, or two photons, or three, or a million. Each possibility contributes to the final answer, so you're summing an infinite number of terms, and that sum is often infinite. This sounds like a disaster. But for electromagnetism, there's a mathematical trick called renormalization. Here's how it works. The infinite terms can be absorbed into the definitions of physical constants, like the electron's charge and mass. You measure those constants in experiments, plug in the measured values, and the infinities cancel out. What's left are finite, incredibly precise predictions. Quantum electrodynamics predicts the electron's magnetic moment to 1 part in 10 trillion. It matches experiments perfectly. Renormalization works for electromagnetism. It works for the strong force. It works for the weak force. But it does not work for gravity. When you try to apply quantum field theory to gravity, infinities appear, and they can't be absorbed by renormalization. The problem is technical, but here's the essence. The gravitational constant, g, in Newton's equation, has the wrong dimensions. When you calculate quantum corrections to gravitational interactions, each successive term in the series introduces new types of infinities. In QED, you have a few types of infinities, and you can absorb them into charge and mass. Done. In quantum gravity, you have an infinite number of different types of infinities. You would need an infinite number of adjustable parameters to cancel them all. That's not a theory. That's just mathematics that doesn't work. The calculations produce infinite probabilities, infinite energies, predictions that are literally nonsense. You can't use the theory to predict anything. It's mathematically broken. This is called non-renormalizability, and it means quantum field theory. The framework that works perfectly for the other three forces fails for gravity. Physicists have known this since the 1970s, and for 50 years they've tried to find a way around it. String theory, loop quantum gravity, asymptotic safety, emergent gravity, dozens of approaches. None have succeeded. But before I show you those attempts and why they've failed, let me explain why this matters. Why we need quantum gravity. Because for most of physics, we don't. General relativity works fine. Quantum mechanics works fine. They operate in separate domains. But there are situations, rare, extreme, but fundamental, where both theories should apply. And in those situations, our physics breaks down completely. There are 3 places where we need quantum gravity, 3 regimes where both general relativity and quantum mechanics should apply, and where both theories fail. Place 1. The center of a black hole. When a massive star collapses, general relativity predicts it forms a singularity, a point of infinite density at the black hole's center. But infinite density is physics code for our equations broke down. Infinity isn't a physical quantity. It's a sign that the theory has reached its limits. As matter collapses toward the singularity, it gets compressed to smaller and smaller volumes. Eventually, it reaches quantum scales, sizes where quantum mechanics should apply. But general relativity doesn't include quantum mechanics. It treats matter as classical, so it predicts infinite density. That can't be right. At quantum scales, matter doesn't behave classically. Quantum effects, uncertainty, fluctuations, discreteness should become important. We need a quantum theory of gravity to describe what actually happens at a black hole's center. Does the singularity disappear? Does matter bounce? Does information get preserved? We don't know. because we don't have the theory. Place 2. The Big Bang. Run the universe's expansion backward. Galaxies get closer. The universe gets smaller and denser. Eventually, you reach a point where all the mass energy of the observable universe is compressed into a volume smaller than an atom. Quantum scale. Extreme gravity, both general relativity and quantum mechanics should apply. Quantum mechanics should smooth this out. Maybe there's a quantum bounce, where the universe transitions from a previous contracting phase. Maybe spacetime itself is discrete at Planck scales, preventing infinite compression. Place 3. The Planck scale. There's a fundamental scale in physics called the Planck length, 10 to the power of negative 35 meters. This is the scale where quantum gravity effects become important, where spacetime itself should exhibit quantum behavior. At this scale, Heisenberg's uncertainty principle applies to spacetime itself. Position and time become uncertain. Spacetime should fluctuate wildly, what John Wheeler called quantum foam. General relativity assumes spacetime is smooth, a continuous fabric. But quantum mechanics says nothing is smooth at small scales. Everything fluctuates. At the Planck scale, these fluctuations should be significant. Spacetime should be turbulent, foamy, discrete. We can't test this directly. 10 to the power of negative 35 meters is absurdly small. The Large Hadron Collider probes down to about 10 to the power of negative 19 meters. We'd need an accelerator the size of the galaxy to reach Planck scales. But theoretically, we need quantum gravity to describe spacetime at this fundamental scale. Because at the Planck scale, both gravity, spacetime curvature, and quantum mechanics, uncertainty fluctuations, matter. And we don't have a theory that includes both. Let me be clear about what the problem actually is. General relativity and quantum mechanics aren't just different theories. They're based on fundamentally incompatible assumptions about how reality works. General relativity says, spacetime is a smooth, continuous, deterministic fabric. It's like a rubber sheet. You can curve it, stretch it, ripple it, but it's always smooth. If you know the distribution of mass and energy, you can calculate the curvature of spacetime exactly. No uncertainty, no probability, just geometry. Gravity emerges from this curvature. Objects follow geodesics, deterministic paths through curved space. Everything is classical, predictable, well-defined. Quantum mechanics says, everything is fundamentally uncertain. You cannot know both position and momentum precisely. You cannot predict exactly when a radioactive atom will decay. You can only calculate probabilities. Fields don't have definite values. They exist in superpositions of multiple states until measured. At small scales, nothing is smooth. Everything fluctuates. The electromagnetic field fluctuates. Virtual particles pop in and out of existence. Energy is uncertain over short timescales. Everything is probabilistic, fuzzy, inherently uncertain. The clash. General relativity requires smooth, well-defined geometry, but quantum mechanics says nothing is well-defined at small scales. How can spacetime be smooth if quantum mechanics says everything fluctuates? At the Planck scale, this becomes critical. Energy and time are uncertain. But in general relativity, energy curves spacetime. If energy is uncertain, spacetime curvature is uncertain. So, at quantum scales, spacetime itself should be in a superposition of different geometries. It should fluctuate wildly. General relativity can't handle this. The theory assumes a well-defined metric, a specific geometry. It doesn't have a framework for probabilistic, fluctuating geometry. And quantum field theory can't handle gravity either. Because in quantum field theory, you need a fixed background spacetime on which quantum fields live. But gravity is space-time. Space-time is the thing that's fluctuating. There's no fixed background. This is the fundamental incompatibility. General relativity, smooth, deterministic, classical geometry. Quantum mechanics, uncertain, probabilistic, fluctuating fields. Both correct in their domains, both incompatible at extreme scales. We need a new framework, a theory that's neither general relativity nor quantum field theory, but something deeper that includes both as special cases. We need quantum gravity, and for 70 years, physicists have tried to build it. Every approach has been brilliant, mathematically sophisticated, conceptually creative, and every single one has failed to produce a testable, confirmed theory. Let me show you the graveyard. You've just seen why quantum gravity is necessary. 3 extreme regimes require it. 1. Black hole singularities, infinite density, quantum scale. 2. The Big Bang, all mass energy in tiny volume 3. The Planck scale, where space-time itself becomes quantum. And you've seen why general relativity and quantum mechanics are incompatible. General relativity requires smooth, deterministic geometry. Quantum mechanics demands uncertain, fluctuating fields. At extreme scales, both should apply, but their assumptions contradict. The solution seems obvious. Build a quantum theory of gravity. Treat space-time like a quantum field. Quantize geometry itself. But when physicists tried this, the math exploded. Infinities appeared. The theory became non-renormalizable. So they tried other approaches, radically different ideas, new mathematical frameworks, alternative geometries, string theory. Replace particles with vibrating strings in 10 dimensions. Loop quantum gravity. Quantize space-time itself into discrete chunks. Causal sets, space-time is fundamentally discrete points with causal relationships. Asymptotic safety, maybe gravity is renormalizable at high energies. Emergent gravity. Gravity isn't fundamental. It emerges from quantum entanglement. Brilliant ideas, decades of work, thousands of researchers, billions in funding, and 0 experimental confirmation. Not one testable prediction. Not one observation that distinguishes between these theories. We're theorizing in the dark, with no data, no experiments, no empirical guidance, just mathematics and hope. Let me show you what we've tried, and why it hasn't worked. Act 5. The search for quantum gravity. In the 1960s and 1970s, physicists developed an idea that seemed to solve everything. What if fundamental particles, electrons, quarks, photons, aren't point-like objects? What if they're actually tiny, vibrating strings? This is string theory. Here's the concept. Imagine a guitar string. When you pluck it, it vibrates at different frequencies. Different vibrations produce different musical notes. In string theory, fundamental particles are like that guitar string. A single string, about 10 to the power of negative 35 meters long, the Planck length, can vibrate in different patterns. One vibration pattern looks like an electron, another looks like a quark, another looks like a photon. All particles are the same underlying string, just vibrating differently. And here's the crucial part. One of the vibration modes, spin 2, massless, traveling at light speed, behaves exactly like a graviton. String theory automatically includes gravity. You don't have to force it in. It emerges naturally from the mathematics. When physicists discovered this in the 1970s, they were stunned. String theory seemed to unify all forces, electromagnetism, strong, weak, and gravity, into a single framework. Even better, the calculations are finite, no infinities. The theory is mathematically consistent. String theory looked like the theory of everything. the final answer, the end of fundamental physics. But there were problems. Big problems. Problem 1. Extra dimensions. String theory only works mathematically if spacetime has 10 or 11 dimensions. Not 4. 3 space plus 1 time. 10 or 11. Where are the extra 6 or 7 dimensions? String theorists say they're compactified, curled up so small we can't see them, like a garden hose. From far away, it looks one-dimensional, a line. Up close, you see it's actually two-dimensional, a surface wrapped into a tube. The extra dimensions are like that, curled up at the Planck scale. Okay, that's possible, but it's not testable. We can't see those dimensions, we can't probe them. It's mathematical necessity, not empirical observation. Problem 2. Supersymmetry string theory requires something called supersymmetry, a symmetry between particles of matter, fermions, and force-carrying particles, bosons. Every particle should have a supersymmetric partner. The electron has a selectron, the photon has a photino. Every particle is doubled. We've never observed any supersymmetric particles. The Large Hadron Collider, the world's most powerful particle accelerator, has been searching since 2010. Nothing. 0 supersymmetric particles detected. Theorists keep pushing the predicted masses higher, saying, we just need more energy. But at some point, this becomes unfalsifiable. Problem 3. The landscape problem. String theory doesn't give one solution. It gives about 10 to the power of 500 possible solutions, different ways the extra dimensions can be curled up, each giving different physical laws. That's 10 to the power of 500 different possible universes, a number so large it's almost meaningless. Which one is ours? String theory can't say. There's no principle that selects our universe from the landscape. Some theorists invoke the anthropic principle. We exist in this particular universe because it's one of the rare ones that allows observers. That's not a prediction. That's giving up on prediction. Problem 4. No testable predictions. The strings are 10 to the power of negative 35 meters long. That's the Planck length, absurdly small. To probe that scale experimentally, you'd need a particle accelerator the size of the Milky Way galaxy. We can't build that. We can't test string theory directly. Theorists hoped indirect tests would work. Supersymmetry, extra dimensions affecting particle masses, deviations from Einstein's gravity. None have been confirmed. String theory has been the dominant approach to quantum gravity for 50 years. Thousands of researchers, tens of thousands of papers, Fields medals and awards, and 0 experimental confirmation. It's mathematically beautiful. It unifies forces elegantly. It produces finite calculations. But we don't know if it's true. It might be a mathematical paradise with no connection to reality. Not everyone accepted string theory. Some physicists said, "We're overthinking this. Einstein was right. Gravity is geometry. Let's take that seriously and quantize spacetime itself." This approach is called loop quantum gravity. Here's the idea. In general relativity, spacetime is smooth and continuous. You can zoom in forever and it's still smooth. But quantum mechanics says nothing is truly continuous at the smallest scales. Everything comes in discrete chunks. Energy is quantized. Charge is quantized. Maybe spacetime is quantized too. Loop quantum gravity proposes that spacetime has a granular structure at the Planck scale. Imagine zooming in on a photo. From far away, it looks smooth. Up close, you see it's made of pixels, discrete dots. Spacetime might be like that. Smooth at large scales, but at 10 to the power of negative 35 meters, it's made of discrete atoms of space. These aren't atoms in the traditional sense. They're mathematical structures, loops and networks that represent quantized geometry. Space itself comes in minimum units. There's a smallest possible area, the Planck area, about 10 to the power of negative 70 square meters. There's a smallest possible volume. You can't subdivide space infinitely. There's a fundamental graininess. What this solves: if spacetime is discrete, singularities disappear. You can't compress matter to infinite density because there's a minimum volume. Black holes don't have singularities. They have incredibly dense but finite cores. It takes Einstein's geometry seriously and applies quantum principles directly to spacetime. But there are problems. Problem 1. Doesn't unify forces. Loop quantum gravity only quantizes gravity. It doesn't include the other forces. There's no natural way to incorporate electromagnetism, strong and weak forces into the framework. String theory at least tries to unify everything. Loop quantum gravity just focuses on gravity. So even if LQG is correct, it's not a complete theory of physics. Problem 2. Very hard to extract predictions. The mathematics of loop quantum gravity is incredibly complex. Calculations are difficult. Connecting the Planck scale structure to observable physics is challenging. Theorists have made some predictions, modifications to gravitational waves at very high frequencies, possible effects on cosmic microwave background, but they're subtle and hard to test. Problem 3. No experimental tests yet. Like string theory, loop quantum gravity operates at the Planck scale. We can't build experiments at that scale. We're waiting for indirect effects. Maybe quantum gravity leaves fingerprints in cosmological observations or gravitational wave signals. So far, nothing confirmed. Problem 4. Different versions disagree. There isn't one loop quantum gravity theory. There are several competing approaches: loop quantum gravity, spin foams, causal dynamical triangulations, and they give different predictions. Researchers are still working out the mathematics. The theory isn't finished. Loop quantum gravity is an active research program. Hundreds of physicists work on it. It's a legitimate alternative to string theory. But after 30+ years, it hasn't produced definitive testable predictions either. String theory and loop quantum gravity are the two most prominent approaches. But they're not the only ones. Physicists have tried dozens of alternative ideas, each brilliant, each stuck. Causal, set theory. Spacetime isn't continuous. It's a discrete set of points, like atoms, with causal relationships between them. If point A can influence point B via light signal, there's a connection. If not, there isn't. Spacetime emerges from this network of causal connections. Elegant idea. Mathematically interesting. No testable predictions yet. Asymptotic safety. Maybe gravity is renormalizable, just not at the energies we've tested. At very high energies, near Planck scale, the infinities might go away. This is called a fixed point in the theory's behavior. If such a fixed point exists, quantum field theory of gravity works after all. Active research, promising mathematical hints, not confirmed. Emergent gravity. Maybe gravity isn't fundamental. Maybe it emerges from deeper quantum phenomena, like how temperature emerges from molecular motion. Some proposals suggest gravity emerges from quantum entanglement, the spooky connections between quantum particles. Spacetime itself might be an emergent phenomenon, not fundamental. Fascinating idea. Very speculative. Hard to test. Induced gravity. Gravity emerges from quantum fluctuations of other fields. The gravitational constant g isn't truly constant. It's generated by quantum effects. Interesting. Incomplete. No confirmed predictions. causal dynamical triangulations. Spacetime is built from simple geometric building blocks, like triangles. Glue them together, sum over all possible configurations, and spacetime emerges. Numerical simulations show promising results. Four-dimensional spacetime emerges naturally in some regimes, but extracting testable predictions is hard. The pattern you're seeing, every approach, 1, makes beautiful mathematical sense, 2, solves some conceptual problems, 3, requires physics at Planck scale, untestable, 4, either makes no predictions or predictions we can't measure. We have a zoo of theories, all elegant, all incomplete, none confirmed. For 70 years, thousands of physicists have worked on quantum gravity. Brilliant minds, sophisticated mathematics, decades of effort, and we have zero experimental guidance. Not a single observation that says, this theory is right, that one is wrong. We're theorizing in a vacuum. Literally, despite all this, we're not completely blind. There are observational hints, clues that suggest gravity might behave differently than Einstein predicted under some conditions. Clue 1. Dark matter galaxies rotate faster than they should. Stars at the edges should fly off into space based on the visible mass, but they don't. Either there's invisible mass, dark matter, making up 85% of the universe's matter, or gravity behaves differently on large scales. Modified Newtonian dynamics proposes that gravity's inverse square law breaks down at very weak accelerations. Most physicists favor dark matter, but MOND can't be completely ruled out. If gravity is modified on large scales, that's a hint about its fundamental nature. Clue 2. Dark energy. The universe's expansion is accelerating. Galaxies are moving apart faster and faster. This requires some kind of repulsive force or energy filling space. We call it dark energy. It makes up 68% of the universe's energy content. But we don't know what it is. It might be Einstein's cosmological constant. It might be a quantum field. It might be a sign that general relativity is incomplete. Dark energy is the biggest mystery in cosmology, and it might be telling us that gravity doesn't work the way Einstein thought on cosmic scales. Clue 3. Anomalies in spacecraft trajectories. The Pioneer spacecraft, launched in the 1970s, showed a tiny, unexplained deceleration. Not much, but measurable. This turned out to be thermal radiation from the spacecraft, pushing it backward. Not new physics, but there are other small anomalies. Flyby anomalies, where spacecraft gain or lose a tiny bit of speed during Earth flybys. These might be instrumental errors, or they might be hints of something deeper. Probably not, but maybe. Clue 4. Tensions in cosmology. The Hubble constant, the rate at which the universe expands, has two different measured values depending on how you measure it. Local measurements, using supernovae, give one number. Cosmic microwave background measurements give a slightly different number. This might be experimental error, or it might mean our cosmological model is missing something. Maybe dark energy evolves over time. Maybe gravity behaves differently on different scales. We don't know yet. These clues are subtle. They might be nothing, but they're all we have. Without direct access to Planck scale physics, we're looking for tiny deviations from Einstein's theory. Hints that gravity is more complex than we think. So far, general relativity passes every test. It's frustratingly perfect. But somewhere, in black holes, in the early universe, at quantum scales, it must break down. Because general relativity and quantum mechanics can't both be complete. They contradict at extreme scales. Something has to give. We just don't know what. You've just seen the graveyard of quantum gravity theories. String theory. Elegant, includes gravity automatically, requires 10 dimensions, and supersymmetry, neither observed. No testable predictions after 50 years. Loop quantum gravity quantizes spacetime directly, eliminates singularities, but doesn't unify forces. Very hard to extract testable predictions. Other approaches: causal sets, asymptotic safety, emergent gravity, all mathematically interesting, all stuck without experimental guidance. Why is this so hard? 4 reasons. 1. Gravity is 10 to the power of 42 times weaker than other forces. Quantum effects only matter at Planck scale 2. We can't shield gravity or isolate it for experiments 3. We have zero data from extreme regimes, black holes, Big Bang, Planck scale. 4. Maybe spacetime isn't fundamental. Maybe we need a conceptual revolution. We have clues, dark matter, dark energy, cosmological tensions, but nothing definitive. We're stuck, theorizing without experiments, building mathematical castles with no empirical foundation. This is the most honest admission physics can make. We don't know how gravity works at the deepest level. So what does this mean? Why does it matter that we don't understand gravity? What's at stake? What comes next? And what should you take away from this? Let's talk about the implications. The philosophical weight. The future of physics. Act 6. What this means. So we don't understand gravity. Why does that matter? This isn't just an academic curiosity. This isn't just a gap in some theoretical framework that only matters to physicists. Understanding gravity means understanding reality at its deepest level. Here's what's at stake. The origin of the universe. What was the Big Bang? Not, when did it happen? We know that. 13.8 billion years ago. General relativity predicts a singularity, infinite density, infinite temperature. But that's not a physical state. That's the theory failing. Quantum gravity should tell us what actually happened. Did the universe bounce from a previous contraction? Did it emerge from quantum fluctuations? Did time itself begin at the Big Bang? Or was there something before? We don't know. We need quantum gravity to answer this. The fate of the universe. Will the universe expand forever? Will dark energy rip it apart? Will it collapse back on itself? General relativity gives us scenarios, but they depend on dark energy, which we don't understand. Dark energy might be related to quantum gravity. It might be telling us that gravity behaves differently on cosmic scales. Understanding quantum gravity could reveal the universe's ultimate destiny. What happens inside black holes? When matter falls into a black hole, where does it go? Does information get destroyed? Does it escape somehow? Is there a singularity or something else? These aren't abstract questions. They're about fundamental laws, conservation of information, the nature of space-time, whether physics is deterministic. Quantum gravity should resolve this, but we don't have the theory. Whether space-time is fundamental. Is space-time the deepest level of reality? Or does it emerge from something more fundamental? Quantum entanglement, information, something we haven't imagined? This question reshapes our entire understanding of existence. Space and time might not be real in the ultimate sense. They might be like temperature, useful descriptions, but not fundamental. A unified theory of physics. The dream of theoretical physics is to unify all forces into one framework, a theory of everything. We've unified 3 forces, electromagnetism, strong, weak, in the standard model. But gravity doesn't fit. Until we solve quantum gravity, we can't have a complete theory of physics. We have 2 separate frameworks, general relativity and quantum mechanics, that contradict at extreme scales. That's not satisfying. That's not complete. That's not the final answer, and there might be practical implications. Quantum gravity is far beyond current technology, but so was quantum mechanics in 1925. And now we have computers, lasers, MRI machines, solar panels, all based on quantum mechanics. If we understand quantum gravity, maybe we could manipulate spacetime. Quantum communication through curved spacetime. New energy sources, technologies we can't even imagine. Probably not. Probably the energy scales are forever beyond reach. But maybe. Understanding gravity isn't just about satisfying curiosity. It's about understanding the universe, its origin, its fate, its fundamental nature. And we're stuck. We've been stuck for 70 years. That's humbling. Let me emphasize how strange this situation is. We use gravity every single day. GPS satellites rely on gravitational time dilation. If we didn't correct for it, navigation would fail within minutes. We launch spacecraft to Mars, Jupiter, Saturn, calculating trajectories with extraordinary precision. Gravity assists, orbital insertions, landing sequences. We get it right. We predict solar eclipses centuries in advance. We model galaxy collisions. We simulate the universe's evolution from the Big Bang to the present. Gravity is the most used force in astronomy and cosmology. We calculate with it constantly, and we're very good at it. Our equations work to 15 decimal places. LIGO detected gravitational waves that distorted spacetime by less than 1,000th the width of a proton. And we predicted exactly what the signal would look like. We can use gravity with astonishing precision, and we don't know what it is. We can describe how it behaves. We have Newton's equations for weak gravity. We have Einstein's equations for strong gravity. Both work perfectly within their regimes, but we cannot explain what gravity fundamentally is, why mass attracts mass, why mass curves space-time, what mechanism connects them. This reveals something profound about science. Science is incredibly successful at describing how things work, but often terrible at explaining why things are the way they are. We know how evolution works: natural selection, genetic variation, reproductive success. We don't fully know why life arose in the first place. We know how quantum mechanics works: wave functions, probabilities, measurements. We don't know why measurement collapses the wave function. We know how gravity works: curved spacetime, geodesics, Einstein's equations. We don't know why mass curves spacetime. Science gives us predictive power. It gives us mathematical descriptions. It gives us technology. But it doesn't always give us deep understanding of why reality is structured the way it is. That's a limitation. An honest limitation. And gravity is the clearest example. The most familiar force. The most obvious. The one you're experiencing right now as you sit or stand, held to the earth. And nobody, not Newton, not Einstein, not anyone alive today, truly understands what it is. That should inspire humility. Science has achieved incredible things. We've mapped the cosmos, split the atom, sequenced the genome, built computers, cured diseases, but we don't understand gravity. The universe is deeper, stranger, more mysterious than we pretend. And maybe, just maybe, we're asking the wrong questions. What if gravity isn't what we think it is? What if the entire framework, particles, forces, quantum fields, space-time, is incomplete? Here are some radical possibilities that physicists are seriously considering. Possibility 1. Space-time is emergent, not fundamental. Maybe space and time aren't the deepest level of reality. Maybe they emerge from something more fundamental, like how wetness emerges from collections of water molecules. No single H2O molecule is wet. Wetness is a property of many molecules together. Maybe spacetime is like that. At the deepest level, there's something else. Quantum information, entanglement networks, something we haven't conceived, and spacetime emerges from it. If this is true, gravity isn't a force or geometry. It's a side effect, an emergent phenomenon. Some physicists think quantum entanglement, the spooky connection between particles, might be the fundamental ingredient. Space-time emerges from entanglement patterns. This would revolutionize physics. Space and time aren't real. They're useful descriptions, but not fundamental. Possibility 2. The holographic principle. This idea comes from black hole physics. Jacob Bekenstein and Stephen Hawking showed that a black hole's entropy, the amount of information it contains, is proportional to its surface area, not its volume. That's weird. Information in three-dimensional space should scale with volume, but for black holes, it scales with area. This led to the holographic principle. All the information in a volume of space can be encoded on its boundary surface. The universe might be a hologram. Three-dimensional space is a projection of information encoded on a two-dimensional boundary. If true, gravity emerges from information theory. It's not fundamental, it's holographic. This sounds like science fiction, but it's serious theoretical physics, with mathematical support from string theory and black hole thermodynamics. Possibility 3. Multiple gravitons or composite gravity. What if gravity isn't carried by a single type of graviton? What if there are multiple types, each responsible for different scales or regimes? Or what if gravity is composite, not fundamental, but made of other particles or interactions, like how protons are made of quarks? This could explain why gravity is so weak. It could explain dark matter and dark energy as different gravitational interactions. Speculative, but possible. Possibility 4. We're completely wrong about everything. Maybe particles, fields, forces, the entire quantum field theory framework is wrong. Maybe there's a totally different mathematical structure, a different way of describing physics that we haven't discovered yet. This would require a revolution as profound as relativity or quantum mechanics. A complete paradigm shift. It sounds dramatic, but it's happened before. Aristotle thought motion required constant force. Newton showed that force changes motion, not sustains it. Complete paradigm shift. Newton thought space and time were absolute. Einstein showed they're relative. Paradigm shift. Maybe we're due for another one. Maybe gravity is the clue that our framework is incomplete. And maybe solving it requires concepts we haven't invented yet. That's exciting, and terrifying, and honest. So, where are we right now? What's the current state of quantum gravity research? Let me be blunt. We're stuck. We have multiple competing theories: string theory, loop quantum gravity, and others. Each has brilliant researchers, sophisticated mathematics, and decades of development. But none have produced a testable, confirmed prediction. We can't distinguish between them experimentally. We don't know which, if any, is correct. We're theorizing without data, building mathematical frameworks without empirical guidance. That's not ideal. Science works best when theory and experiment dance together. Theory predicts, experiment tests, theory adapts. In quantum gravity, we have theory and no experiment. We're dancing alone, but there is hope. The next generation of experiments might provide clues. Gravitational wave astronomy, LIGO, Virgo, and the future LISA space-based detector might see quantum gravity effects in black hole mergers or early universe events. Black hole observations, the event horizon. Telescope and future instruments might detect deviations from Einstein's predictions near event horizons. Cosmic microwave background. Future satellites might detect signatures of quantum gravity in the universe's oldest light. Particle accelerators. The Large Hadron, Collider, and future colliders might find indirect hints, extra dimensions, supersymmetry, new particles. Quantum experiments in space, testing quantum effects in microgravity, might reveal quantum gravitational phenomena. These are long shots. Quantum gravity effects are expected at Planck scale, far beyond our reach. But maybe, there are observable consequences. Or maybe not. Maybe quantum gravity is forever beyond experimental reach. Maybe the Planck scale is nature's locked door and we'll never have the key. If so, we'll need a conceptual breakthrough, a new way of thinking, a revolutionary idea that reorganizes our understanding. That might take decades, or centuries, or it might never happen. Physics isn't guaranteed to solve every problem. Nature doesn't owe us answers, but we keep trying. Because that's what science is, the pursuit of understanding, even when the problem seems impossible. If you remember nothing else from this, remember this. Gravity is the most familiar force in the universe, and we don't understand it. Not, we don't understand it perfectly. Not, there are minor gaps. We fundamentally don't know what it is. Newton gave us equations. They work beautifully, but he admitted he couldn't explain the mechanism. Einstein gave us geometry, spacetime curvature. Brilliant. Confirmed. But doesn't explain why mass curves spacetime. Quantum mechanics unified the other three forces, but gravity won't fit. The math explodes. Every attempt at quantum gravity has failed to produce testable predictions. And that's okay. This isn't a failure of science. It's the frontier, the edge of human knowledge. Science doesn't claim to have all the answers. Science is honest about what it knows and what it doesn't. We know how gravity behaves. We use it every day. GPS, satellites, space missions, all based on gravitational calculations. But we don't know what it fundamentally is. That's the paradox. That's the mystery. That's the honest state of physics. The bigger lesson: reality is deeper than we imagine. The universe is stranger, more mysterious, more complex than our current theories capture. Gravity, the force that holds you to this planet, that shapes galaxies, that governs the cosmos, is not fully understood. And maybe it won't be understood in our lifetimes. Maybe it requires concepts we haven't developed. Maybe it's beyond our reach. Or maybe someone watching this video, someone young, curious, mathematically inclined, will have the revolutionary insight that cracks the problem. Maybe the next Einstein or Hawking is out there, waiting to make the breakthrough. That's the invitation. This is an open problem. The deepest unsolved mystery in fundamental physics. The Holy Grail. If you're drawn to it, study physics, study mathematics, learn quantum mechanics and general relativity. Then push beyond them. Because gravity is waiting. The universe is waiting. The answer, whatever it is out there. Let me zoom out one last time. Let's see the full journey. Newton, 1687, gave us the universal law of gravitation, predicts everything from falling apples to planetary orbits, but couldn't explain how gravity works. Einstein, 1915, gave us general relativity. Gravity isn't a force, it's curved spacetime. Mass bends geometry. Objects follow geodesics, confirmed by light bending, time dilation, gravitational waves, black holes, but doesn't explain why mass curves spacetime. Quantum mechanics, 1920s to 1970s, unified three forces: electromagnetism, strong, weak, into quantum field theory. Each force has particle mediators. Predictions match experiments to extraordinary precision. But gravity doesn't fit. When we try to quantize it, math explodes. Infinities appear. Non-renormalizable. 70 years of attempts, string theory, loop quantum gravity, dozens of other approaches. Brilliant ideas, sophisticated mathematics, zero experimental confirmation. The problem: gravity is weak. Quantum effects matter at Planck scale, impossibly small. We can't probe it. We can't test theories. We're stuck. And that's where we are. The most familiar force, the most used in astronomy, the one shaping the entire cosmos, and we don't understand it. But here's the thing. You are experiencing gravity right now. As you sit or stand, held to the earth by a force that nobody fully understands. Every moment of your life, you're interacting with a fundamental mystery. The universe is pulling you toward its center through a mechanism we can describe but not explain. And that makes every moment, every breath, every step, every heartbeat, a reminder that reality is far more mysterious than we admit. We live in a universe governed by a force we don't understand. That should fill you with wonder and humility, and maybe a bit of excitement, because the universe still has secrets, deep secrets, and gravity is the deepest. One day, maybe in our lifetimes, maybe not, someone will solve this. Someone will figure out what gravity truly is. They'll unify quantum mechanics and general relativity. They'll explain what happened at the Big Bang. They'll tell us the universe's fate. And when that happens, it will be one of the greatest intellectual achievements in human history. But until then, we wait, and we wonder, and we're honest about what we don't know. Gravity, the force that shapes the cosmos, the force we use every day, the force we still don't understand. And that's the most honest thing physics can say.